Hello, this is Team CH4. We are Needham High School's 9th grade's CubeSat team. Welcome to our final presentation for the 2026 Build a CubeSat Challenge, and our CubeSat is called the CorkSat. I am Karan.
I'm Christos.
And I'm Aiden.
Our mission is to examine, determine, and analyze the frequency of meteorite impacts in the lunar South Pole for 3 years to help gather data about the lunar surface for the upcoming Artemis missions. It will be mostly conducted in the lunar South Pole region, specifically at the 9 possible locations for the Artemis 4 landing site. As the CubeSat is orbiting around the moon, it will take pictures of the landing sites via imaging the surface of the moon to detect new craters.
Our CorkSat as a system is relatively simple, consisting of a Raspberry Pi at the heart as C and DH cables connected to an IMU, antenna, and camera. The power subsystem, which provides continuous electricity, consists of a solar panel, a controller for it, and a battery to hold charge for eclipses. When the CorkSat is orbiting the moon, it will take 3 end-to-end pictures of the Artemis area of interest on the south pole of the moon once every orbit. The data then shall be compressed and sent to one of 3 ground stations on Earth for processing. We will show our complete CorkSat operations in 5 steps. These 5 steps are powering up, imaging, image analysis, battery, and transmission. First, we will show the CorkSat powering up. In this demonstration, the CorkSat shall power up before being put into orbit, where it will then be switched into autonomous mode to conduct the rest of these steps. A person shall manually turn on the CorkSat when in the presence of red, blue, and green LEDs before being put on the rocket to go into orbit. Our demonstration will show that the CorkSat is able to activate to complete its mission of capturing images of the lunar surface. Here's the video.
From power on, the CubeSat shall start itself and all of its subsystems.
Next, the battery demonstration. In this demonstration, the CorkSat shall change itself using its solar panels when it is facing the sun. We have set it up so that the CorkSat shall be exposed to sunlight while the green lights are flashing, which is the indicator of the battery being charged. Our demonstration will show that the CorkSat can be powered via sunlight using the solar panels while conducting the mission. Here's the video.
Third, we have imaging. In the following video, the CorkSat shall take a clear picture of a mock lunar surface, pause to simulate subsequent orbit, and take another picture of the lunar surface at the same location, but with a new crater. The demonstration shall prove that the CorkSat is able to take sharp, frame-to-frame photos of the lunar South Pole, allowing later image alignment and pixel analysis of the frequency of impacts on the South Pole. Here's the video.
So now, we have taken the photo using the CubeSat, and the processing will be done on the ground station for efficiency.
Here are the 2 images taken by the CorkSat. As you can see, image number 2 is a new crater, where image number 1 is not. Up next, we have a transmission demo, including ground station operations and radio frequency transmission.
In the video, the CorkSat shall, using solely Bluetooth, transmit a compressed demo image to model ground station 10 feet away. Our demonstration will prove that our CubeSat is physically able to transmit to a simulated ground station in the S-band frequency range using Bluetooth. In the next slides, we will prove using our link budget that the CubeSat is theoretically able to transmit data to a location approximately 384,400 kilometers away. Here's the video.
The CubeSat shall use connections from the ground and the Earth to the Moon in order to send data it has. Now, the CubeSat has connected to the Earth station, and we move it over to the Moon. The CubeSat on the Moon has now sent the data, and we have received it. I'll just unpack the data, and we'll be good to go. Extract all. And boom, we have our image sent from our CubeSat via our radio waves.
We already answered that practically. Yes, we can send data in S-band. However, we need to show that this holds for lunar orbit, given reasonable assumptions. Our link budget proves this. We use 3 ground stations in the US, Spain, and Australia to provide the maximum coverage for our CubeSat. We selected the lowest S-band frequency range for our uplink frequency because it is a more power-friendly option while still being in the S-band range for the ground stations to pick up. The antenna diameter and frequencies were found via documentation. We figured out the aperture efficiency using the gain to aperture formula. Similarly, we used a mathematical formula for the uplink antenna power at the feed and the satellite uplink GT ratio. We started at the max bandwidth and decreased it until the uplink carrier to noise ratio was acceptable with the bandwidth, and we compared link budget at different parts of the orbit. Non-diplex means that it does not send data at the same time as it receives data. Because the link budget clearly shows a positive carrier to noise ratio with a good margin, it means that we are able to transmit data at lunar distances. For the downlink, we use similar methods as we did for the uplink. We use link budget calculator online for both the uplink and the downlink.
Lastly, we have the pixel analysis video conducted by the ground station. The demo consists of the ground station conducting image alignment and pixel analysis. The ground station shall use the 2 images of the lunar surface in demonstration 3 and conduct tomography to align the 2 images. Then, using a Python program, the CubeSat shall detect any pixel changes between the 2 images and output an image detailing where the differences are. The demonstration illustrates that the ground station can compare multiple images and analyze the frequency of impacts on the lunar south pole through spotting new meteorite impact pixels in the images. Now for the live demonstration.
As you can see, I have 2 images loaded that have been taken by our CubeSat. Notice how one has the extra mark. We have a problem. We want to compare these images, but they are ever so slightly misaligned in both color and in physical alignment. The solution to this is a combination of SIFT, FLAN, and homography, which aligns the images and compares them pixel by pixel. To illustrate, I'm going to first click Run Comparison. The software will find features in both pictures that match each other. These features will be used to compute a matrix that describes how one image can be warped to the other. These features will be after the matrix is computed, it is refined using an apply and refine algorithm. These images are warped to be aligned, and then their color gradients are matched via histograms, which is a representation of the colors of the image. This yields the result, which clearly identifies the difference between the 2 images.
Here is the pixel analysis in comparison to the images taken in step 3. We tested the discharge rate of the satellite in normal operation, meaning a 120-minute stretch of suboptimal sun followed by a 13-minute eclipse period. On the graph, the eclipse period drops off steeply, showing that our solar panel was in fact generating a significant amount of solar energy. However, the solar panel is simply too weak to sustain the CubeSat because the solar panel is 1 watt while the Pi consumes 2.5 watts. In addition, we conducted a ground sample distance demo. Here's the video.
We created our own GSD testing board specifically for the demo, and while putting that up against the wall, we slowly moved the CubeSat backwards while it was capturing a video of the board in order to gain references to calculate the GSD.
We use a formula for distance to find the distance between the camera and the paper, yielding 1300 millimeters. Our ground GSD is calculated from the real size on the paper and the pixel width in the photo. As we calculated that 15 pixels represents 5 millimeters, so the ground GSD was 0.33 millimeters per pixel. Using the scale factor found by dividing the orbital height by the ground tested height, we scale our ground GSD to the orbital GSD, yielding 41 meters per pixel. In conclusion, we calculated that our GSD is 41 meters per pixel, which satisfied our SMART goal of the GSD being below 50 meters per pixel. For our power test, the red, blue, and green LEDs were all seen to light up, indicating that the subsystems are able to light up and maintain proper function. In our power demo, green lights indicating the charging of the battery started flashing after the CubeSat was exposed to sunlight for less than a minute, indicating that the CubeSat is able to charge. For imaging, the CubeSat was successful in taking 2 clear images of the mock lunar surface, allowing the ground station to take pictures to analyze and determine the frequency of meteorite impacts. In the transmission demonstration, we showed that data could be transmitted, allowing for the ground station to function. The data analysis demo, key pixel differences between the 2 photos were able to be detected, allowing users to detect new craters on the moon. Altogether, these demos make sure that each subsystem works for the mission.
Because of the time limitations, we could not improve our false positive rate. We see it as negligible for the time being, as there would be a human analyzing whether the false positives are real craters or not. If we had more time to improve upon our final project, we would set reducing the amount of false positives as our utmost top priority. In the power test, we used an LED lamp instead of sunlight, which has a different wavelength than the sun, the power source we are using. We also had some other issues, such as the fact that homography, which we were directed to use, does not work in the 3D curvature of the moon. Several changes need to be made to scale the CubeSat to a flight spacecraft. It shall have an aluminum shell to protect it from space, an antenna to communicate with the ground, thermal regulation systems to keep parts within specifications, an upgraded camera, thrusters for orbit insertion, and reaction wheels for attitude management. It shall have a battery with a larger capacity to survive lunar eclipses. When we say lunar eclipses, we mean when the Earth blocks the moon. This is important because these can have a significant impact on battery lifespan and are fairly common. We use a lithium iron phosphate battery as they are significantly safer and can last more cycles. In addition, due to our findings from the previous slides, the solar panels must be upgraded to provide adequate power to the system. Despite the extra moving parts, we believe the best choice is using fold-out solar panels due to the extra power it gives.
As explained before, our operation site is near the south pole of the moon, specifically between 90 plus minus 6 degrees latitude. The reason why we did not use an NRHO eccentric orbit was because we were concerned that the CubeSat would go too fast, which affects image quality. We achieved our orbit through a paper by the AIAA that lists multiple orbits that are the most stable in a 3-year period. And we found an orbit for the paper that was both low and stable, which is perfect for imaging. Additionally, we specifically chose an inclination angle of 90 degrees because that is the optimal angle for taking the clearest images over the South Pole. We ran simulations and tests on SDK to verify that it could stay in orbit for the full 3 years of the mission. We learned that software can be more difficult than hardware to troubleshoot. Additionally, we learned that parts, especially acrylic ones, require lots of care when handling. Finally, we learned to balance the factors going into choosing an orbit, such as GSD or stability. The CubeSat should also be tested frequently in order to catch bugs early. Finally, future missions should all use resources such as papers on the matter they are researching. Thank you for listening. Any questions?
I have a question. That was an excellent presentation. Can you talk about some of your software development challenges, specifically how you dealt with the early on corrupt image download that you were experiencing?
Yeah, so the image download problems was mostly due to the fact that the code was transmitting in packets, which were getting corrupted because of various issues with the code, such as it not timing out. It listens for times, it timed out on the timer. So we addressed this by going through the code and thinking like, hey, This code needs to have a proper timing scheme. It also needs to increase to decrease the amount of time it takes to send. It also needed to just start the connection and then start sending packets like that. The system we had was that it would start a connection, it would send a packet, then it would close this connection and start it again, which was inherently inefficient.
Do you think some of that problem could have been solved if you had transmitted things over Wi-Fi versus Bluetooth, which is what you use?
Definitely, because Wi-Fi can be much more stable in such matters, especially if we're going through something like GitHub. However, we believe that Bluetooth is a more accurate assessment of the actual how the satellite would behave
Yeah.
in orbit because it uses S-band.
Great. Very good. Thank you.
And Jeff here with a question. So you talk, and very nice, by the way, presentation. You're looking at meteor impacts, and you show one, that's great, but you didn't really talk about what size impact are you guys trying to detect? Maybe I missed that, but are you trying to detect, meters, tens of meters, kilometer size? Over.
We want to detect them in like the 1 to 10 meter range because that's like where they're most common. But like that are also still visible to camera in orbit. We talk about it in scaling, but we do need a more powerful camera in order to be able to detect such crater impacts. So as this is just a prototype, it doesn't really matter.
Okay, so good. And you showed a discussion of image resolution. So do you believe that your camera, that what you showed in your picture would be scalable to the lunar surface?
We do believe that our tests can be scalable to the lunar surface since they are utilizing this like the same underlying software and the same underlying logic that they would use in
Very
orbit.
good, thank you.
I was gonna ask a similar question about the resolution of your camera. If you said it was on the 40-meter scale, if I remember correctly, then that would have limited the size of craters you could observe. So, but you guys answered that, so great job.
Thank you.
Thank you.
All right, thanks.
And finally, our first place winners. This team demonstrated excellence across all aspects of the challenge, from design and testing to communication and teamwork. Please give it up for CH4. Let's give them a round of applause.